Okay, ladies and gentlemen, today we are going to talk a little bit about Avogadro's number. We have the same learning target that we have had, and that learning target is right here. Describe how a mole is used in chemistry. We're going to keep on doing this learning target for a while here, folks, because when I turn to our success criteria, our next slide, our I can, or our objective, it shows that we are going to be converting between the mass, the moles, and the number of particles of a substance. Now, we're even going to add more to that because we're going to go into volume and density also. But for now, our objective is to convert between the mass, moles, and number of particles of a substance. Today, we're not even going to do mass, all right? We're just going to focus on particles of a substance and moles. Now, look at this slide that I have here, telling us about some certain endings here, okay? Atoms, we have atoms, molecules, formula units. Now, when we're dealing with these, ladies and gentlemen, all right, we need to use the proper terminology. So if I have a single element, okay, I am dealing with atoms because it's going to be important. Tomorrow, we're going to talk about two-step Avogadro problems. Today, we're only going to do single-step Avogadro. Tomorrow's two-step. So we need to know the difference between formula units, molecules, and atoms. So if I have an atom, I'm dealing with an individual element. Now, if I have a molecule, okay, it goes back to bonding. What did we call molecules when we talked about bonding? Anybody remember? If it was a molecule, what type of bonding did it use? Covalent bonding. And if it were a formula unit, what type of bonding did it use? Ionic. Okay? So when I see something formula units, I already know that it is ionically bonded. When I see something molecule, I know that it is covalently bonded. So when I get here, 1 mole of carbon is equal to Avogadro's number of carbon atoms. 1 mole of glucose, C6H12O6. 1 mole of glucose has Avogadro's number of molecules of glucose. 1 mole of sodium chloride has Avogadro's number of formula units of sodium chloride. Now, one thing that people always tend to struggle with, and I'm going to show you right here. If I have 1 mole of O2, I'm going to have Avogadro's number. I'm going to have Avogadro's number, but what am I going to label it? Do I label that an atom? Okay. Is that a single element? Okay. It is oxygen. I would agree with you. But what do we know about this bonding of oxygen right there? We had the molecule kits. We've seen oxygen. Is that bonded together, O2? What do you think? Absolutely. Okay. If you remember, O2 is a double bond. All right. So we've double bonded 2 oxygens together. So how would you classify it? Would you classify it as an atom? No. Would you classify it as a molecule? Absolutely. So this is right there. 1 mole of oxygen has Avogadro's number of molecules of oxygen. Okay? So even though it's only 1 element, okay, it's it's covalently bonded together. They're sharing electrons, so we classify that as a molecule. So any of our super 7, okay, any of our, we call those diatomic molecules, okay? Why are they diatomic molecules? Because they are covalently bonded together. All right. So it's important to be able to distinguish between molecules, formula units, and atoms. Now, when I switch to my next slide, okay, I have here what I call my flux capacitor. And if you look down here where I've got this little arrow thingies here, it says representative particles. Now, that is kind of a cover-all of everything. Representative particles. If I say representative particles, it could be atoms, it could be formula units, it could be molecules. But if you're doing a test or a quiz and you don't know, and you say, I'm going to get away and get around this by just putting representative particles, okay? It should be labeled molecules, but I'm going to put representative particles. You're going to miss points, okay? You're going to miss points because we don't use representative particles as a label. I've seen it done before, okay? But we don't do it in here. We don't put particles. We don't put representative particles. When we have Avogadro's number and we're using it, we use either an atom, a molecule, or a formula unit, okay? Now, this is what I call the flux capacitor. And when we're dealing with the flux capacitor, we have representative particles, we have moles, we have mass, and down here we have volume. We're only going to be dealing today with one part of the flux capacitor, and it's going to be that right there. We are going to be using Avogadro's number to convert back and forth from representative particles to moles and vice versa. So, how are we going to do that? Well, ladies and gentlemen, I'm going to open up a brand new slide here because I want a blank slide. I don't know where it put into my little thing. All right, there we go. We're right where I wanted to be. I want a blank slide because we have to talk about conversion boxes. When we do these molar conversions, we need conversion boxes. So, what is a conversion box? Well, if I had 2.5 dozen, let's say I have 2.5 dozen donuts, all right? I want to convert that to see how many donuts I actually have. I set up a conversion box as so. Now, the key to my conversion box, whatever I put here on the bottom has to cancel with my dozen right there. What do I mean by that? Well, if I have 2 over 2, what does that equal? 1, right? If I have 10 over 10, that equals 1. What if I have a dozen over a dozen? What does that equal? 1. Okay? So by having the dozen over a dozen, I get that to cancel. So when I'm doing my conversion box, I'm looking for things to cancel. So I am going to put the dozen on the bottom. So if I have 1 dozen, what does that equal to? Well, 1 dozen is equal to 12 donuts, right? And that's the whole idea of the conversion box. They are equalities. They are equal. Even though they're different units, they are equal. 1 dozen is equal to 12 donuts. So when I would do my math here, my dozen cancels, so my label is going to be Donuts, because that's what I have left here up at the top. My label is donuts. So I'm going to take 2.5 and I'm going to multiply it by 12 because I multiply what's on the top. So what's 2.5 times 12? 12, 24. 24 and 6 is what? 30? So I'm going to get 2.5 dozen is going to be equal to 30 donuts. Okay, you've done a conversion. You've used now, folks, a conversion box to convert from dozens to donuts. Now, let's do another one, okay? Let's do another one. A little bit different, okay? I have 50 quarters. I have 50 quarters, and I want to know how many dollars 50 quarters are. Well, once again, I'm going to set up my conversion box. And what do I want to cancel? What do I want to cancel? Quarters, right? So I know that I have to have quarters on the bottom, and I'm going to dollars. Well, what's my conversion? I know that $1 has 4 quarters, right? $1 is 4 quarters. So, as I do, my quarters will cancel. So my new label is going to be dollars. So, what I'm going to do is I am going to take 50 times it by 1. Now, people actually do this in their calculator. Do you need to do that step? What's 50 times 1? 50. You don't need to do that step. And then I'm going to divide it by 4. So really what I'm doing is I'm taking 50, I'm dividing it by 4, and when I do the math, I come up with 12.50. So, if I would have 50 quarters, I would have $12.50. All right? Nice, easy conversions. You can do that, right? Well, now we're going to do the same exact thing, folks, except for we're going to be using Avogadro's number, which is a very, very big number. So when I come back here, to my flux capacitor, I'm going to set up a conversion box right by this arrow. This arrow is running from representative particles all the way up here to mole. So if I have representative particles and I want to convert it into moles, I'm going to have 1 mole on the top, and on the bottom, I'm going to have Avogadro's number. Now, I don't have any labels here because my labels are going to change. I could have 1 mole of carbon. That would be Avogadro's atoms of carbon. I could have 1 mole of glucose. That's going to be Avogadro's number of molecules of glucose. Okay, so I'm not going to put labels on there. When I go this way, when I go from moles to representative particles, I'm going to have my conversion box, just like I had before. 1 mole is going to be on the bottom, and Avogadro's number is going to be on the top. So those are my equalities in my conversion box that I'm going to use to do these problems. Okay? Now, I don't even use the flux capacitor. I've been doing this a long, long time. The flux capacitor is something to help you out, folks. It's a visual to help you to go from one to the other. So, what I have is I have this thing memorized in my mind. If you're taking a test or a quiz, you're not going to be able to use the flux capacitor. But you know what? I've seen a lot of quizzes that got turned into me where the person has drawn the flux capacitor on it. Okay? So that's fine, but you're not going to be able to use your flux capacitor on a test or a quiz. Now, what I would recommend here, ladies and gentlemen, is that you write this down in your notes, because we're going to be working problems. You're going to eventually, at one time or another, struggle at something. And when you do so, folks, you're going to come up and ask me, and I'm going to say, go grab your notes. We'll look at the examples we've already done. Now, if you don't copy down these examples in your notes, you're not going to have anything. Okay? You're not going to have anything to look at. So what we need to do is make sure we copy the examples. So go ahead and copy this down in your notes. I'll give you a second here to copy it, and then we'll do the problem. Now, my problem states, how many formula units are in 2.84 moles of barium chloride? Well, I can see right now that I have formula units. So that tells me I'm dealing with ionic bonding. I can see that I have 2.84 moles of barium chloride. So when I go back to my flux capacitor, I'm right here. I have moles. I need to go down here to representative particles. So I am going to use this conversion factor right there. So Avogadro's number is going to be on the top, and the mole is going to be on the bottom. So when I come back here and I look, I say, okay, I have 2.84 mole of barium chloride. I'm going to set up my conversion box. And when I set up my conversion box, what do I want to cancel? What do I want to cancel? Hunter? Moles, right? So I'm going to have moles of barium chloride down at the bottom. Well, I know that 1 mole of barium chloride has Avogadro's number of formula units of barium chloride. Fit that all in that little box. Now, if I did it right, I have a mole of barium chloride over a mole of barium chloride. That equals 1, doesn't it? So that label cancels out. It's going to leave me with the label of formula units of barium chloride. Now, when I'm doing my math in my calculator, I am taking 2.84 and I'm multiplying that by Avogadro's number. Okay? So I'm multiplying that by Avogadro's number, and I come up with a value with 1, 2, 3 sig figs. I always go back to the number I was given in the problem. 3 sig figs, I'm doing multiplication here, so I still stick with 3 sig figs. That tells me 1.71 times 10 to the 24th. And I put a box around it so Mr. Braun knows exactly where my answer is. Now, what I like to do, ladies and gentlemen, when I'm doing this is something that I call ballpark it. Okay? When I'm doing math in chemistry, I ballpark stuff. And what I mean by that is, if I have 2.84, that's pretty close to 3, isn't it? Okay? Well, if I would take 3 times Avogadro's number, okay, 6 times 3 is 18. So this is going to give me 1.8 times 10 to the 24th somewhere. Is my value that I got close to that? Yeah, so I ballparked it okay. That's what I call it, ballparking it. Just looking at my numbers and saying, okay, does that make sense? Because if I'd have got a number that was, 1.7 times 10 to the 30th, I'd say, whoa, that's pretty far off of what I thought it should be. I'm not in the ballpark. What did I do wrong? So I just mentally ballpark it and look at that to help me determine, okay, is my number where it should be around that area? Yes, it is. Okay. Now go ahead and copy this down, and then we're going to work this here in a second. The question states, how many moles are in 2.02 times 10 to the 52nd atoms of iridium? Well, I've got the mental picture, okay? I've got the mental picture in my mind that says I'm at atoms of iridium. I'm not familiar with iridium, so I come over here. Iridium is just like I thought, capital I, lowercase r, all right? So I have atoms of iridium. I'm down here visualizing my formula units, okay? Excuse me, my atoms of iridium, and I've got to go up to moles, which is in the middle. So I'm visualizing that, and I say, okay, I have 2.02 times 10 to the 52nd atoms of iridium. Now, I am going to draw my conversion box, and I know that I want atoms of iridium to cancel. So I'm going to put atoms of iridium on the bottom. Well, I know my conversion factor is Avogadro's number of iridium atoms is equal to 1 mole of iridium. I go back and I have atoms of iridium here on the top, atoms of iridium on the bottom. I get a cancellation, like I should. So now, my new label is going to be mole of iridium. Now, like I said before, okay, as I'm looking at this, 52 minus 23 is what? 19? Does that sound right? 52 minus 23 is 19.
Teachers, pardon the interruption, but if I could have the following students for a moment: Ethan Howard, Mackenzie Perry, and Rihanna Norton. Thank you.
No, that's somewhat bigger. It's 33. My bad. 52. Wait. 52 minus 23, Braun. 52 minus 23 is 29. So when I have, excuse me, when I have my number for this, okay, when I have my number for this, it should be somewhere around the exponent of 29. I'm ballparking that in there. So what I'm going to do is I'm going to take 2.02 times 10 to the 52nd, 2.02 times 10 to the 52nd, multiply by 1, and then I'm going to divide by Avogadro's number. And it's going to give me the answer of, with 3 sig figs, 3.35 times 10 to the 28th. So I was close to that 29 that I ballparked it in at. So I'm going to square that up here. All right, I'm going to square that up here, and that is my answer here. Now, one thing that I haven't talked about, ladies and gentlemen, is how do I work my calculator? Because, ladies and gentlemen, we're going to run into problems, okay? We're going to run into problems if we do something like this. when I have Avogadro's number and I plug it into my calculator, people want to hit the times button. Then they want to hit the 10. And then they want to hit the caret. And then they want to hit the 23. And they say that this is Avogadro's number. Well, the problem with that, folks, is that if I follow the order of operations, I could get screwed up. Well, why? Well, what if I take certain values and do it like this? I'm going to become off, and usually it's off by a decimal place. Okay, my decimal is one place too far to the left or to the right. So what we have to do is we have to know how to program our calculator. So look at your calculator, okay? If you don't have your calculator out, take it out, look at it. You have an exponential button on your calculator. Most of the time, it's the second function of the button above the 7. So find the button above the 7, which is probably a comma. When you are doing Avogadro's number, type in 6.022, hit second function, the EE button, and it should give you a little e, right? And then type in 23. That is scientific notation in your calculator. All right? That is scientific notation in your calculator. Make sure that you use that E button, please, because it'll screw everything up if you do not. Here's another example. Go ahead and copy this example down. We're going to work this one. Then I'm going to have you work your own example, and we'll answer it. How many molecules of carbon dioxide are in 0.64 moles of carbon dioxide? I'm dealing with molecules, so I know that I have covalent bonding going on. I look at my flux capacitor. I see them at moles, and I'm going down to representative particles at the bottom right. So I start off with 0.614 mole of carbon dioxide. I set up my conversion box. I know that I want mole of carbon dioxide to cancel. So 1 mole of carbon dioxide. On top, I'm going to put Avogadro's number of molecules, because that's what I'm converting to. Avogadro's number of molecules of carbon dioxide. A mole of carbon dioxide over a mole of carbon dioxide is equal to 1. That'll cancel. Leaves me with the label molecules of carbon dioxide. Now in bronze process, right now is where I ballpark it. So I look at this number right here, and I say, okay, 0.6, that's a little bit more than half, 0.5. So a little bit more than half. So this, my value that I calculate should be a little bit more than half of my 6.022. So I'm expecting it to be a little bit more than 3.011 times 10 to the 23rd. I get my calculator. I type in my values, my 0.614. I multiply that by Avogadro's number, and I come up with a value of, with 3 significant figures, 3.70 times 10 to the 23rd. That was just a little bit more than my ballpark value, so I'm in the range that I expected to be in. I'm okay. Now, one thing that I have not mentioned, ladies and gentlemen, look at your calculator. Look at that number that you just calculated there. It says 3.697, blah, 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 right? A bunch of numbers afterwards. You would be surprised, folks, at how many people write down the answer as being 3.70. You know why? Because they look in their calculator and they miss that little e on the back end of it. Do you see how that could be easily done? Okay, it is. Because a lot of people do it. So make sure when you're doing this, you check your calculator on that back end to see if there's a times 10 to the something you have to add in. Okay? Now, something else too. I had this happen last year for the first time, and I ended up having to count this wrong because the young man that kept doing it would not adjust. We are not calculators, okay? So this is not an appropriate answer for that. Even though your calculator says e to the 23, that is not appropriate for our answer because we know that that is scientific notation. And our scientific notation is a times 10 to the 23rd. So if you're going to put that e to the 23rd in there, you're going to miss some. Because that is not how we signify scientific notation with the e. We use the times 10. Now, what I would like for you to do, folks, is here's our next example. I want you to work this example, and then when you're done working it, we are going to work this as a group. So go ahead and do it on your own, then we'll work it as a group. If you run into a stumbling block, raise your hand. I'll come help you through it. Okay, now, as I get onto this one, 1.91 times 10 to the 19th formula units of ammonium NH4 chloride. Now that's a pretty bad writing there. Let me redo that little OCD in me. NH4Cl. That's a little bit better. I get on to you guys for not writing legibly. I'm going to do it. So here we go. I have my conversion box, and I know that I want formula units of ammonium chloride to cancel. Well, I know that. I have Avogadro's number of formula units. That is equal to 1 mole of ammonium chloride. I get my formula units at top, formula units at bottom to cancel. My label is going to be mole of ammonium chloride. Now I just have to do my math. When I ballpark it, like I was doing with Hunter back there, I have 19 and I'm dividing it by 23. Those are my exponents. So 19 minus 23 is going to give me somewhere around minus 4. So I should be in that area, and you're going to see it's going to be a minus 5. Okay? Go ahead and take a break. We'll finish this when we get back from break. Okay, so now I'm doing my math. 1.91 e to the 19th, and I'm going to divide that by Avogadro's number. And I come up with a value. I ballparked it at minus 4. My value actually came up to be 3.17 times 10 to the minus 5. Dang it. Now I box in my numbers so Mr. Braun knows exactly where my answer is. Now, ladies and gentlemen, we got a thumbs up here. How'd we do on that? Were we okay? Okay? All right. Now, not just this problem. Are we thumbs up with a Avogadro's thus far? We're going to do 2 steps later on. All right, we'll do 2-step Avogadros tomorrow. We're okay with this one? All right, good.